Morning, everybody. Welcome to another one of our webinars here at Analytics. Today's webinar is going to focus on the automation workflow associated around improving the analytical blanks for elemental sample preparation. So when we look at this as an overall process in how we handle the sample preparation for getting digestion vessels samples ready for elemental analysis by ICP, we don't just have to consider the microwave digestion or the actual preparation of the samples. We've really got to look at this as a path and a workflow of what happens at the start and at the end of this process. Today's webinar hopefully is going to cover some of these key areas for you, primarily looking at the ultra pure acid supply, reagent handling, and the vessel cleaning aspects of this process. So when we are looking at these certain factors here, it really falls into three main categories of the areas that we've got to do to help control this analytical blank. And when we talk about the blank, it is in relation to making sure that we are providing the best quality digest or solution to meet the needs of the ICP analysis. In the world that we live in now, with regulations, with improvements to obviously the technology in terms of the analytical, it puts a lot more stress on the front end sample preparation procedures. So in here, we're going to focus firstly on the purity of your reagents and what impact this can have for you moving forward and getting a good quality digest with a low blank. So this trace level determination we know is greatly impacted by reagent purity. There really are only two options available to analysts, and it is to either purchase high cost ultra pure acids that are very low in metals, or to distill your own. So the platforms that we're going to have a look at first of all here are the SubClean and the DuoPore. So these milestone products have been on the market for a number of years. They're very proven technologies, and both of them work from a sub-boiling distillation technique. So this sub-boiling distillation has been demonstrated over years to be the best method really of purifying acids. So what we do is to take a reagent grade acid, and then we gently vaporize the surface of this acid, typically at about 20 degrees below its boiling point. In comparison to a conventional way of purifying acids that relies on a heating mantle to heat a reactor to then obviously purify the acids, the sub-boiling technique prevents any formation of spray, any droplets, and yields a very, very high purity of acid. So not only does it give you a on-demand supply by purchasing low-grade reagent acids and purifying them to ultra-pure, it also has a huge cost-saving implication as well. Typically, a lot of the users will save upwards of 90% on their monthly spend of acids. So it's a very important technique and a very important part of the process to try and get a handle on from the laboratory point of view. If we look at the schematics of the two platforms that we discussed, so first of all, I'll have a look at the DuoPore system. Now, the DuoPore is a two quart still systems. It can come as a sub-pure, so you may see this in some literature, but essentially that just means there is a single quart still instead of two quart stills placed in the chassis. They both operate exactly the same way. So this schematic here shows us really what's going on. So we have a large quart still, and in the top left corner you can see a little funnel, so that's where we fill the acid into. So we place the reagent grade acid into this quart still, and then number one on this schematic is a infrared heating element. So this is what is used to gently vaporize and heat the reagent grade acid so that we don't get any bubbling, spitting, or transference of the contaminants from the reagent grade acid into the distillate. So in each of these stills, there are placed two infrared heating elements. These will be controlled by the control terminal based on the power that is required to distill the acid that you will be using. Now, typically within here, we focus on the used acids such as nitric, HCl, hydrogen peroxide, ones that are typically used in higher quantities for acid digestion. So we have the infrared heating element creating the heat, evaporating up the purest form of the acid from the solution base, And then in this instance here with the duopore or the subpure, we have a cold finger condenser that runs through the middle of the quartz still. Now, this cold finger probe is connected to a water supply. We would typically recommend a recirculating water bath or recirculating chiller for this, because one, it will save a lot in terms of utility costs and water costs, but also it can control to lower temperatures and provide a better disparity between the heat and the cool at the top. So what this does is to basically act as a condenser and a trap. So as the acids are heated, they will come up and condense onto the cold finger, they will drip down, and then they will go into the high purity PTFE, PFA collection bottle at the bottom. So it's a very simple process, but one that's very easily operated and one that can be run overnight. If we look at the subclean, it's a very, very similar setup. The main difference being here is that the condenser in this process is not a cold finger condenser, but an air-cooled condenser. So on the left of this schematic, you'll see 3 bottles. All of these are high purity PTFE collection bottles. So the one at the top is used as a condenser. Number 2 is actually placed underneath the heating element, so similar to the infrared heating element you can see on the duopore. And then number 3 is the collection bottle. So what happens in this instance is that the number 2 bottle is filled with the reagent grade acid. And once that is heated and the evaporation occurs, the pure forms of that acid, instead of hitting a cold finger probe, will travel up into the air-cooled condenser, reflux, and then they will drop down into the collection bottle at the bottom. So a very similar process, but instead of using cold finger probe, it is using an air-cooled condenser. Now, both of these platforms come with the same rugged control terminal. So this is a compact touchscreen color terminal. It's designed to be used overnight, so unattended use. So the programs that are stored within here have been designed as such that as soon as they are finished, they will turn off and cool down. These method libraries are based on the requirements of the acid. So if we were using nitric, HCl, within there, we set the limits of the power to ensure that the boiling points are, or the heating is below about 20 degrees of the boiling points of these acids, just to make sure that we're not heating them too much and creating sort of splashes, transference of the impurities from there. The control terminal also will operate a pumping system for us. So this is one of the newer features of the platforms. Previously, the user had to manually load these and manually pull these out of the stills themselves. But now we've moved to automating this process, and it provides a much safer mode of operation for the platforms and reduces any exposure of the users to handling the acids. So the way these pumps work is the same for the subclean as it is for the subpure and duopore. Consists of 3 components really. So on the left of this schematic, you can see a filling bottle. So this filling bottle is what will actually contain the acid that you're wishing to distill. So this is placed in there and capped, and then it's connected to the pumping system. And in between here is what we class as a buffer bottle. So the buffer bottle's main need is just to protect the pump system. So when we're wanting to fill the system, we will have the PTFE tubing placed in the P position. And what this will do when we press the fill button is to force the acid into the chamber of the subclean and the duo. Once that's filled, we press start and we run the process based on the acids we're trying to distill. Between acids, you will want to do a cleaning procedure. So if you are just using the same acid, you can keep filling, maybe routinely every month to look at doing a cleaning procedure. But if you are only distilling one acid, say nitric, you can just keep refilling the chamber. If you're doing a cleaning procedure, obviously we need to drain the chamber and the lines entirely. So the way we do this is to then place the tubing from the P into the V section of the pump, and this creates a vacuum. So it basically reverses the procedure for loading, and it will pull out the acid and anything in the lines. And this is really where the buffer bottle comes into play, because if any droplets were to get through, they would drop into the buffer and not actually get in touch with the pump. It is recommended between switching acids to do a cleaning run with water. So once you evacuated the chamber of the acids, take the bottles out, rinse them, fill with water, and then follow the same procedure as you were for distilling acids, and then you can move on to the next acid easily from there. So in terms of the purity and the quality that we can expect from here, it's essentially is incredibly high. So these figures here are concentrations in ppt. So as we can see, for a lot of these major elements here, we've got incredibly low levels actually in the acids, which allow us to achieve these very low blanks when we're actually doing a digest and the subsequent ICP analysis. There are two columns on here referring to a single distillation and double distillation. So just to give a bit of background on there, is that we can heat these samples a little bit quicker if we're not looking for the ultra pure grade of acid, because obviously the acid and the blanks are really determined by your analytical needs. So if you are looking at incredibly low trace levels, you would want to look at having very low impurities in your acids. If you are just looking for a better quality of acids to help lower the blank, but not meet any regulatory requirements, then often a single distillation can be enough. And single distillations really are done at a faster rate. So the yield will be slightly less, but the purity there is obviously affected because we're trying to heat the acid a little bit quicker. You can do double distillation where you do two single distillations. So you take the first single distillation from a reagent grade acid to a pure acid, and then you actually take that pure acid and do a distillation on that. Often we find it's easier just to do a slower heating profile of the reagent grade acid to try and achieve these double distillation needs. And it just saves the user having to switch over the collection bottle and refill the chambers within there, but both options are available. In terms of a comparison of the hardware and the technology here, the difference really between the subclean and the duoport is the productivity. So the rate at which we can actually distill the acid. So you can see here the subclean is able to do 80 mils an hour, the duoport up to 400 mils per hour. Now the duoport one is if you were using two stills, so each still can actually do 200 mils an hour. So if you've seen the literature about sub-pure, that would have a maximum productivity of 200 mils per hour. Now, the big difference, or the reason for the difference in the productivity here, is to do with the cooling system. So the subclean doesn't require an external chiller or a cooling supply. It just uses the air cooling to create the disparity in the reflux, as we saw. The duoport obviously needs the cold finger in there, which helps in terms of productivity. So you can actually produce obviously more per hour within here, but you do have to factor in that you would need an external chiller or a cooling device for that. The stills themselves, as I mentioned, the subclean is a single, so you only can do one acid at a time, as is the sub-pure. If you have the duoport and two independent stills, these can process two acids at once, so you could actually run nitric and HCl at the same time if you required. One of the advantages of the subclean, although the productivity is lower than the sub-pure and the duoport, is that it is compatible with HF. And this is because all of the components are high purity TFM. So obviously the duoport and the sub-pure have a quartz distillation chamber. So if we were to place HF inside there, it would obviously start to erode the still itself. So we can't process HF. Neither of the systems really are recommended to work with sulfuric acid just because of the nature of sulfuric's boiling point is very high. We would probably have to heat it in excess of 300 degrees to start the distillation process, and there is TFM components in both systems which wouldn't really be able to handle this acid. But in terms of the more commonly used ones like nitric, HCl, HF, if you've got subclean or hydrogen peroxide, these can all be processed depending on which platform you choose. In terms of footprint, the subclean is smaller, so it does take up less space on the bench than the duoport. And with the duoport and the sub-pure, there is a chiller that you would obviously have to factor in to place under the bench within there. So if you're looking for a compact solution, the subclean can offer benefits there. In terms of the method library and the pumping system, these are exactly the same. So it's the same control terminal, same method libraries and methods that we would use within there. and the pumping system is identical. Although it is an option, we tend to always include it on there. In terms of cost of investment as well, the sub-clean is obviously a lower initial cost compared to the sub-pure and the duo-pour. And when we're looking at this in terms of investment and savings and return on this investment, it's a very easy calculation to look at for a laboratory based on the spend of their ultra-pure acids and what they're buying in. Now, these figures here were taken from the Fisher website recently. So we look at nitric and HCl because they are the two most commonly used and in the highest volumes. And when we compare the grades per litre cost, the ultra pure, £1,500 to £1,600 compared to £30 to £35 of the reagent grade. So it's very easy to see where we can quickly start to save money and get a good return on investment for the laboratory. So if we use an example here running 50 samples a week and roughly 10 mils of acid in each of these samples, the cost savings on here are considerable per month. So typically to make 2 litres of ultra pure grade, we would need 3 litres of the reagent grade. So the savings there are up to nearly £3,000 per month. We can do a return on investment for individual cases. So if it is something you want to have a look at with your reps, please do get in touch with them after this webinar, and we can look at a more tailored return on investment calculation for you. But generally speaking, this allows you to pay back anywhere between 3 and 6 months based on the platform that you're investing in. So obviously the sub-clean has a lower upfront cost compared to the sub-pure and duo-pour, but even so, a return on investment of 6 months or under is pretty incredible, and it's often one that is quite easy to put forward to finance or your accounting colleagues to look if you're going to be bringing this in-house. So the advantages obviously within here are the cost savings, but also having on-demand supply as well, so not having to wait for deliveries of ultra-pure acid at all. So we've had a look at the purity of these reagents and what they can do in terms of the blank and how they affect it. But also we need to consider any errors that are occurring during the reagent addition. Now, this is something that typically hasn't really been looked at too much in the past, but it is a part of the process that is quite often tedious and unpleasant. Anyone that's done this, it is a manual step. Several drawbacks associated with it, because when you are adding acid into the digestion vials, there are safety concerns, obviously, because users are exposed to acid vapors, even when done in a fume cupboard. There are risks of splashes, either from the Winchester or pipetting. There's a risk of contamination from the fume cupboards in general, but also from human error as well, whether they haven't quite put the Winchester in the right position or haven't fully loaded or dispensed the acid in, or whether they're using pipettes that maybe aren't as precise. All of this coupled with the fact that it's time consuming. So if you're running with a 40 to 44 position carousel, it can take the best part of an hour to actually add these reagents into the vials themselves. So there are a lot of drawbacks in terms of the reagent addition. One solution to this is Milestone's latest technology, which is the Easy Fill. Now, this is an automatic dosing station. Essentially removes all of the issues that we saw associated with the manual addition. So we improve safety, we improve consistency. As it's automated, workflow is dramatically improved, and there's a very high flexibility in terms of what you can actually place inside the chassis of the Easy Fill. We take a little closer look at what this offers. So the dosing compartment itself, as you'd expect, is made of anti-corrosive polypropylene because there's going to be acids obviously in the cavity itself. There is a built-in exhaust with a dedicated filter, which means that this doesn't have to sit within a fume cupboard either. So there is an exhaust hose that connects to the back that can lay into a fume cupboard or an extract, allowing the Easy Fill to sit nicely and safely onto a lab bench rather than taking a valuable route in a fume cupboard. All of the acid contact parts as well are made of high purity PTFE, which makes it compatible with any acids that you wish to process. The way that it operates is to essentially use a peristaltic pump to dispense these acids from their containers into the vials that are going to be holding your sample. for digestion. So this peristaltic pump has a set dispensing speed of 1.5 mils per second, so it's very fast, but it is very controlled as well, with an accuracy greater than 99%. Working ranges, we can operate between 0.5 mil and 50 mil. This typically covers almost all of certainly acid digestion requirements, because you wouldn't be filling typically more than about 10 mils of acid at a time. But it can be used post-digest to top up autofill ICP autosampler vials. So if you are requiring higher volumes, the software can be updated and changed to allow higher dosing of these, but the typical and standard working range is 0.5 mil to 50 mil. So we've got 6 channels that we can work with, which means we've got 6 reagents that we can connect to the top. The standard bottle top GL45s are supplied with the system. You can place any of the vials or vessels that fit on top containing your acid. Typically, we would always leave one of these channels for water, because we use this to flush and to change in between acids. But there is full reagent compatibility even for HF for running within the EasyFill. There is a waste drain into a carboy, so there's an easy disposal of the waste and the rinse solutions. And the software itself tracks the reagent volumes, so you can see when you're getting low in terms of the acid supply. And it also tracks the waste volume and alerts you if the carboy is getting full, to allow you to easily change that over and dispose of it. In terms of what you can actually do within the EasyFill, it fits all applications relating to digestion. So obviously, as we would expect, the milestone digestion vessels are all compatible, even the legacy ones. So older platforms, whether it's SK10, SK15, the Maxi rotors, there are rack systems available for all of these, as there are for our single reaction chamber platform. So the racks and vials for the UltraWave 1 and 2, the UltraClave, and also for the new UltraWave 3 are all available. We can also supply ICP autosampler vials, so you can do your dilution post-digestion automatically as well. And these come in a variety of racks and sizes. But we can also accommodate non-milestone digestion vessels, racks and vials as well. So if you are using a digestion system that is not for milestone, the EasyFill can still be utilized in your laboratory, and we would just need to know the rack sizes, positions, and we can supply the appropriate adapters. Now, in terms of automation, we can see where the EasyFill obviously offers a lot of benefits, but in terms of improving your analytical blank, there's a factor within here that often is overlooked, and that is the disparity or the bias you can get from the manual dispensers. So we do have a full technology report on this, which supplies a lot more data that I'm showing on this particular screen. And this dives into a lot more based on different acids and the bias that is seen between an EasyFill and the bottle top dispensers. Now, this particular example here is just to highlight really for some of the major elements the difference between manual addition and EasyFill and where this can affect your blank. So as you can see on here, there's significantly better bias in favor of EasyFill in terms of less impurities getting placed into the digestion vial before digestion. So this can play a big part really in wanting to achieve these ultra trace levels. So not only through automation and safety, but also through the reproducibility that EasyFill offers and the cleanliness it offers in terms of switching between acids, can have a real impact on the blank and the outcome of your results. So just to pull that together in terms of the EasyFill, obviously we know it covers a lot of areas in terms of workflow from the automation of the process. It also allows the operator a lot more time to go and do other tasks. So if they're saving 40 minutes each run in terms of loading the acids into the sample, then they can go off and do other things and come back and knowing that EasyFill has accurately dispensed and filled all the vials to the required limits. The reliability, as we've seen, is very high, so very limited risk of contamination, removes the human error side of it, and a very precise and reproducible filling from the peristaltic pump. Enhanced safety is obviously a huge thing here because there is no direct contact with the acids or exposure to acid vapors when you're actually loading these in. So rather than having to stand manually in a fume cupboard, filling one by one, This is all done completely safely in a closed chassis with a built-in exhaust. Flexibility as well, so it's suitable for reagent addition as said at the start, but also for diluting before the sample vials go to the ICP. And the compatibility with milestone and non-milestone rotors and racks means that it really can fit into any laboratory that's using microwaves or sample preparation devices. So the third factor within here is really how the vessels that you're using are affecting your blank as well. Now, in terms of the microwave vessels, they have a propensity to retain the waste gases that are generated during the run. Now, typically, most microwave vessels, especially if you're working in the trace level, you'll be using high purity TFM and not PFA vessels. Either way, these vessels themselves, because there is a lot of pressure generated during the run and there is a headspace of acids created during the run, these will seep into the walls of the vessels during the run and maintain there after the run. So cleaning microwave vessels is a critical component really to ensuring that you're not getting in transference of these waste gases from run to run. So maintaining the cleanliness is essential not only for the blank quality, but also for safe operation as well. It can often occur that if you haven't got clean microwave vessels, that you will get heating occurring of the Teflon itself, normally in the neck of the vessel. And this is due to people not cleaning the vessels from run to run, where they're getting this contamination of the NOx getting trapped in the top of the Teflon. And what this leads to is over temperature, over pressurization, and poor reproducibility of results. What it also does is reduce the lifetime of the vessel significantly as well. So you will start to run into replacement cost of these vessels a lot more if you're not actually cleaning your vessels or maintaining them properly. Now, the manual cleaning methods are very laborious. They also do increase user exposure to acid. So if we were to follow a US EPA method, you would have to soak your microwave vessels in litres of nitric acid at 80 degrees, then transfer them into another base where you would have litres of HCl within there. So there's a lot of exposure to, one, the acids, but also the vapours. And it also is a very, very long process that takes often hours and hours to do. So this really creates a bottleneck as well as increasing obviously the likelihood that the user is going to be exposed to acids. So the solution to this is our TraceClean platform. So the TraceClean is essentially an automated acid steam cleaning system. So we use this to clean not only the Teflon microwave vessels, you can use glass, quartz parts, even ICP torches within here. Anything within the laboratory that you want to clean that's made of Teflon, glass or quartz. It's very fast, so within an hour you could have cleaned your vessels within here. And because it's a completely closed system with its own built-in exhaust, there's no operator exposure to acid vapors, and the TraceClean doesn't have to sit in a fume cupboard either, so much like the Easy Fill. There is no cooling water, there's no chiller required, so we simply rely on the powerful fan that's built in to allow us to cool. And then we've got the same rugged terminals we use for the subclean and the duo port to help to control the system and also store any methods. So the way it works is to utilize the same subboiling technique as we saw in the subclean and the duo port. The difference here is that we have an acid reservoir at the base. So this acid reservoir is filled with reagent grade nitric acid. Now, typically we work with about 500 mils of acid within there. We have a ceramic heater underneath here that is going to sub-boil the nitric acid. So it's going to heat it to 20 degrees below its boiling point. Within the chamber itself, we have hollow glass rods that we will place the vessels or the items to be cleaned over the top of it. So what happens here is the ultra pure acid comes up through the base of the reactor. It will pass up through the hollow glass rods, and then it will hit inside of the vessels that we want to clean. And in here, it will be cooler. So we have a reflux. So this acid hits there, takes all the contaminants, drop the contaminants back down into the reservoir, and then only the pure form of that acid comes back up. So anything that's washed away or is clean stays in the acid reservoir. And then as the cycle goes through its process, we'll have about 5 to 6 refluxes within the hour or the hour and a half, depending on what your method you choose. And then you have very clean items left over at the end. So the pumping system used to fill and empty, the system is the same for the duopore and the subclean. The chamber itself can accommodate up to 20 positions. So typically we would work with these hollow glass rods. We can have different sizes of these if we've got different heights of equipment that we want to clean, but we can also put the funnels. So if we're doing smaller caps that say belong to our SSE technology or to vial tops, or we can put the tridents in to allow us to actually get 3 prongs into each of these 20 position chambers to increase capacity for maybe smaller vials wishing to clean. So there's quite a high capacity that we can accommodate within there. And it really does make this your perfect accessory for sample preparation. So it automates, it improves the blanks, and it increases the lifetime of your vessels, all the while reducing the operator exposure to acids. So in terms of what we looked at today for the factors to control this blank and to automate your workflow, the purity of your reagents can be controlled by our subclean or duopore subpure platforms. In terms of reagent addition, we have the example of the easy fill that can help to automate and to improve blanks. And then finally, in terms of the vessels and how they affect the blank, the cleanliness can be improved and automated from our TraceClean platform. So in terms of resources that we've got available to you, we have a lot of technology reports that will highlight the needs and the real world sort of situations of our platforms. So if you do want to have a look at these, contact your reps and we can send these out. We also have user profiles to show how it is changing laboratories across the globe. And we also have an ebook that's available called Think Blank. This is a very detailed book looking at the backgrounds into all these factors and exploring them in much greater detail. So this copy is available free. Again, if anybody did want to have this, then please do contact us after the event. So that draws us to a close there of our webinar looking at the clean chemistry solutions we've got. In terms of Q&A, we'll leave it open for a couple of minutes and I'll see whether anybody's going to put anything in the chat box. We've got a couple coming in here. So the first one is asking about solvent use for the easy fill. Yes, although we focused mainly on acid digestion today because it's really relating to the elemental path flow or the workflow within there, you can actually process solvents in the easy fill. Now, we wouldn't recommend having one platform that had solvents and acid use because you would run into issues in terms of making sure all the lines were clean. But if you did want a dedicated platform for acid and a dedicated one for solvents, then the easy fill can actually accommodate that. One more on the TraceClean here. So how much acid is used and how often do you need to change the acid? So as I said, typically we would put in about 500 mils of the reagent grade acid. We never switch between nitric, so we only ever use nitric to perform the cleaning and the purification here. It's probably consumes around 30 to 40 mils every run. So periodically, maybe every month, if you are using it on a routine basis, you would want to drain it and then do a water clean and rinse through the system and then refill with the acid. But you will need to top up between runs. 500 mil is the optimum, but anything approaching 200 mil won't be enough to actually create the condensation that we need inside from there. So typically, yeah, you're using about 30 to 40 mils of the reagent grade acid. So it's a very low cost solution within that. And the final, how long does it take for the run? So with the TraceClean, typical run is about an hour. If they are vessels that are heavily contaminated, you may need to do what's classed as the more thorough cycle, and that will be about an hour and a half. The cleaning cycles can be about 45 minutes. So it is still very quick, and typically an hour is enough time to be able to get the cleaning done. And one of the other benefits that I should have mentioned on there is that once it's finished, it is actually dry. So when you're actually handling the vessels at the end. Obviously, you need to use gloves and everything, but they won't be drenched and soaked. That's it. So I think that's all. If there are any other questions, we'll try and get to them after, but we're sort of approaching the time now where we'll draw this to a close. So thank you to everyone that's attended. We will be obviously continuing our webinar series throughout the year, and we'll be sure to send out the invites from there. So thank you very much for joining today, and have a good rest of your day.